and like just one problem, just like this on the final, start to finish, work it all the way through. So I'm entertaining that concept. 16,000 pounds. Yeah, I'd have to. Yeah. So, and I wouldn't be able to grade that on building itself. In other words, if you make a mistake in the statics, somehow you don't come up with 8,000 on each side, everything's going to be wrong. But I would look at what you did with the numbers you got from the previous step. And if you did it right, then you get full credit for that. So yeah, when you have a build up problem, you can't, I don't think personally you can't do that to people. Like, that's not right. Because they're doing the problem right. They just made a mistake early. Yeah, exactly. Which we know we're all capable of. So it's dug for a beam. It's 6 by 20 inches, 16,000 and 10-foot span. Yep. Directly to the center. And this is called a simple beam. So that's important because the moments at the ends are equal to 0 on simple beams because those ends are free to rotate. So when we get to the very last step, we'll do deflection in the very end. So hello, Ruth. How are you? All right. We are working a problem from the statics all the way through, like kind of a real world. This would be a real world problem. This is what we would do, right? If we were given this situation, like, hey, we got a 6 by 20 beam. This is how it used to go when I worked for Keywood. I'd be sitting in my office. In walks the mechanic and says, hey, we got a 6 by 20 beam. We're going to put 16,000 pounds on it. Is that okay? And I would say, all right, go away and come back in a couple hours and I'll tell you. So that's what we're doing. All right, so the statics part's pretty easy because we got this centered up 5 feet and 5 feet. So we have 8,000 and 8,000, right? So the quest would be to determine like, is bending okay? Is shear okay? And deflection. So I should look up what they use for deflection. A lot of times it's a triangle. I don't remember what they used. Area moment method, they do Y A to B. We're not doing that. And I'll just look. Yeah. They use like a triangle, a delta for deflection. So to get this, right, we're going to need the maximum bending moment. And to get this, we're going to need the maximum shear force. Then we can go for the stresses. So typically, you're going to want to do that with diagrams. So a V equals 0 diagram, M equals 0 diagram. What's the shear do? Yep. Then it comes across, nothing happens, hits the 16, comes down, and then heads back up. Oops, comes across, nothing happens. I keep wanting a distribution on there. Right, where this is 18 or 8,000 pounds, and this is minus 8,000 pounds. So when we're looking for V max, we're looking for the biggest number, absolute value, biggest number. So V max is 8,000 pounds. All right, moment diagram. Yeah, so it's plus here, right, in the shear. So that's our slope, and then it's negative there. So it's going to start with positive slope, and it's a straight line because we know that step is from horizontal straight line to slope straight line to a curve. So slope it up and then it goes negative slope. Where the shear crosses zero, we have a maximum moment. Couple ways you can get that moment. You can section the beam, right? And then calculate the beam moment and then resist the beam moment with the internal moment, which flips the direction. Or you can just use the shear diagram. So if the shear diagram is that simple, just do an area of the shear. That's the way to go about that. So we know we have 5 feet here and we have 8,000 there. So 5 and 8. $40. And units are foot, pounds. Right? We just did the area of that thing. 8,000 times 5. All right, now we can move to bending stress. So this is an analysis problem. We have the beam, it's 6 by 20. We have the load condition, we have everything. We're just analyzing the situation. A design problem would be, we don't have the beam, but we have the load and the condition. We just need to size the beam, okay? So analysis design, the whole first part is the same. You do all of this, whether it's analyze or design. We have to have the load condition. We can't design something without the load condition, right? We got to know the span, we got to know how much load, we got to know the geometry, and we have to be able to work through the statics part. But you can do all that without the beam. We haven't used 620 and Doug Fir at all so far, right? So analysis says, okay, we know what it is. We just need to verify that the bending stress is within the limits and the shear stress is within the limits and the deflection is within the limits. All three would make this okay. There's actually some other ones, but we don't need to go that deep, right? That's more than enough. So let's work towards bending stress. That equation was what? M over SX or MC over I. That's exactly right. M over SX. Either one. So if you're given the beam, now we know we can look up SX. That's called the section modulus. And all it is it takes C and I and figures it out for you, right? So you could take I and C and divide I by C and you would get the SX out of the table. So it's literally just a little formula that they put in the table when they printed it out to help us. So our moment is 40,000 foot-pounds. And we need to look up the SX value for our 6 by 20. Six by 20, the biggest one. Yep. SX is 349. Units are inches cubed. Oh, geez. What's the number? I just glitched. 349 inches to the third. So it's a bending stress. We're going to need PSI. So we have to resolve that foot, get it out of there. right? So I'm gonna need a 12 inches per foot. So I can cross these feet out. And one of the inches gets rid of the inches to the third, and I'm left with PSI. So make sure you do that on any problem to make sure you're getting the right unit out of the equation. $13.75. Point, I'll say 36 PSI. I said it's Doug fir. So when you do your first stress, bedding stress, you should check it. Make sure. So in the back, we find the table for typical values of timber construction and Doug fir. And modulus elasticity is 1700. We're looking for F sub B. Yeah. F sub B is 900. Yeah. So the limit is 900 PSI. So we're over the limit. Unfortunately, it doesn't work. It's exactly right. If that's the load condition, so then that's when I go back to them and say, that doesn't work. So you either got to reduce the load, but more than likely they'll say, no, we have to carry 16,000. That's, you know, what the thing weighs or whatever. That's the weight. They'll say, well, what will work? They always do that. Always. Like, oh, okay. I'll go back, give me another hour. I'll go back and figure that out. So how do we figure out, like, okay, this doesn't work. How big does it need to be to work? So then that flips us into design. And with design, we put in the limit for the stress. We put in the value for the moment because we're going to carry that. Right? Because that's the load condition. And then we calculate the section modulus. So the section modulus is the variable that refers to the cross section of the beam. So it's like the area. It's inches to the third. So it's not really an area, but it's a lot like the area. We still need our 12 inches per foot to deal with this foot. So we solve for SX. And we get 533.33. Inches cubed. Yeah. So if you have inches squared, right? Down below. So this is pounds per inch squared. And this is going to move over here in the denominator. So you have inches squared in the denominator, right? So then it flips up to the top and multiplies with this 12 here to get inches to the third. The feet go away. Does that make sense? Yeah. That's some old algebra shenanigans. Yeah, so now we go back to the table because they have told us that they want wood. We find this properties of structural timber, and I'll go back in the 6 category, 6x6. There's the one that we had, 6x20, and that was 349. We need 533 minimum. So it looks like we have to go to 8x material, and 8x22 gets it done. A 10x 20 gets it done. So if 20 was important for the height of the beam, sometimes that is, because that's why they used a 6x20, right? Because they only had room for a 20 or something like that. Then sometimes you'll have constraints like, oh, we got to stay at 20 tall, but we can go wider. Like a 10x20 works, right? That's at 602. But also an 8x22 works at 578. So sometimes you want the lightest beam, and here is a weight per pound. So the 8x22 is 44 pounds per foot. The 10x20 is 51 pounds per foot. They both work, but one's a little lighter than the other. So sometimes that's a constraint, like, hey, choose the lightest beam for us, right? We want the lightest thing in this thing. So yeah. Not always. No. Like a W shape that's, you know, if you use the W shape that's like 18 deep and it's only spanning 5 feet, but it's carrying 30,000 pounds, that beam itself might weigh 100 pounds, 200 pounds at the most, right? So 200 pounds of beam weight compared to 30,000 pounds of load, negligible. Like it's going to be so over kind of designed for the situation, then you don't worry about it. Yeah. Yep. You can go right to it. Like if your SX matches one of these, you can use it like right on it. It's the only ones that have the factor safety already built into that. That's why it's only 900 PSI for wood, for bending. There's a giant factor of safety there. Like people that have worked with wood know how much it'll carry. And then I come along and say, it's got to be a 6x20. And they're like, what the F are you talking about? I'm like, dude, it's got to be. If you wanted to meet code, that's one of the reasons why a lot of contractors really don't like engineers is they think everything's way over designed. Well, it's not us. It's the American Society of National Standards that comes up with these numbers that we have to use. So, but it's also why most of our structures don't just fall down. Like, you know, in other countries, some things just fall down. All right, so let's just go with the 8x22. It's lightest. 578, 8x22. So the choice, 8x22 SX of 578. Is that what I said? 8x22, 578. And this is typically how you do it. If we were worried about beam weight, we would then take the weight of this beam, which is what, 44.8 pounds per foot. And we would plug it back in as a distribution, run through it again, calculate a new bending stress to see if it works still, okay? But since we wanted 533 and what we chose is 578, it's actually substantially more than the 33. And the weight is 44 pounds per foot, which is going to be nothing compared to the 16,000 pounds, right? I wouldn't do it like, oh, it's going to work easy. But you don't know that in the beginning when you're first doing this. It's good to run that back through and just make sure that your bending stress didn't kick you over. Like if this was 534, I'd be like, the weight of the beam might push me over, right? I'm kind of that close to it. So I would go calculate that, or I just wouldn't choose it that close. So, all right, good, super good. Let's now do shear. So the three things: bending stress, shear stress, deflection. So now we need the shear equation, and we have a solid rectangle, so there's a shortcut for that. So shear for a solid rectangle is 1.5 V over A. Pretty simple. It's essentially the old P over A from chapter 9. Load over area with a 1.5 factor. So, yep, that's V max. Always, these are always maxes. M is max, V is max. So 1.5, RV is 8,000. And our area, we should look up 8 by 22. Yep. Didn't have the chart, we could just do an 8 by 22 because that's bigger. You could, you'd be safe on that. Right. Yeah, if you used a bigger area, yeah. But if you Google it, it'll give it to you immediately. And you'll have, like wherever you go to work, if you're doing this kind of stuff, they'll have everything for you from that kind of stuff. All right, what'd you get for shear stress? Yeah, 74.53 PSI. Always super low, very rare that it's driven up. We always check it though. And then what's the allowable for shear stress for Douglas fir? It is horizontal shear 180. So it's pretty low, 180 compared to 900. I mean, wood does have those weak fibers in it that kind of drive it down, but this is okay. Because it is less than the 180. All right, now the last piece is deflection. So I'm going to introduce you to the beam diagrams, and you're going to be interested in shooting me, but that's all right. Because I really have to have you learn it first before you get the diagrams, because all the diagrams aren't there. These are the common diagrams you can have. And if your beam does not fit a diagram perfectly, you got to do it just like we did it. You got to do it by hand. Everything, right? So if your diagram fits one of the conditions in the book, then you can do it by formula, and you can do everything by formula. Yeah, so what we're looking for is a simple beam, so supports at the end with a concentration in the middle, right? That's our load condition. Simple beam, supports at the end, concentration in the direct middle. If we can find that beam in the back of the book, then you can use the formulas. Yep. Yeah, this is big. This is a big page. This is a happy page. Yeah, so this is what the beam formulas are. It's got to match perfect. And the mistake the students make is, oh, this one's really close. It's like, nope, doesn't work. But if it matches perfectly, you can get everything. You can see that R equals V. So we just read this beam over here. You can see that R is the reactions, right? And V, that's shear. So R equals V under this condition, which is exactly what we found. We found maximum shear to be 8,000. Okay, so let's just keep working down. M max is at the point of the load for this beam, which is what we found also, right, with our diagrams. And the equation is PL over 4, where P is the load and L is the span. So you would not have to do the diagrams because here they are, right? They produce them for you. But you could just go for maximum moment with PL over 4, which is what we got. Then there's always other conditions. So the other conditions are MX. So if you want the moment at some X location for some reason, you can use this equation. right? So that's what this whole X is out here. And then we can get deflection. Delta max, that's deflection at point of load. That's where the maximum deflection occurs. And you can kind of see the beam deflecting, right? It's going to do this convex thing. No, concave thing. Convex is humped over. Still trying to learn that. But it's at the load, and we have to run this equation. PL cubed, 48, that's a constant. E, what's E? Yeah, Maslow's elasticity. So the material is important. If this was a beam that was a W shape, that's steel, right? This is a beam that's wood, it's going to deflect differently. So the material property has to come into the deflection equation, has to. And what we use is E, the modulus elasticity, and then I is area moment of inertia. Okay, so let's run this equation because this is what we want, delta max. So yeah, potentially, or I might want you to work it out and draw the diagram for me. So yeah, could be either way. Now that you know about them, use them for sure. If I give you something that matches the back of the book, use them. If I give you a problem that says draw the shear and moment diagram, then you got to draw it. And that's probably not going to match the back of the book. All right. So what do we have? PL cubed. P, I'm going to make my L like that. Cubed over 48 EI. So P is the load, 16,000 pounds. L is the span. And we're going to have to keep track of the units. It does not do that for us. So 10 feet, or I could put in forward thinking, right, 120 inches. Right, because I know I'm going to have to work with E, which is going to be in PSI inches, and I, which is going to be in inches. So just right away turn my span into inches. Modulus elasticity for Doug Fur. Yep. 1700 KSI, but above I have pounds, right? So I need to like figure that out. So what would that be? 17, gonna add 3 zeros, E to the 5th. Should work, right? Because I'm adding 3 zeros. I'm keeping the 17. So I'm gonna end with 5 zeros. That's E to the 5th. Then now that's gonna be pounds per inch squared. Right? Okay. And then inertia. What is the inertia for my new beam, which was a 8 by 22? Whew, that is a big inertia. That's huge. It's a big beam. 8 by 22, you're right. Yeah, sorry. 6210. And what are the units? Inches to the 4th. So let's resolve these inches, because I'm guessing what should deflection be? That should be like in inches, how much it actually is moving, deflecting. So pounds go away, and inches squared and inches to the 4th resolve to inches squared down below, and I have inches third up above, so I do have inches left over. So that's good. Now I just have to see if I can run my calculator correctly with all these big powers.
0.0545.
Yep. So I'm just gonna write 5 inches, so 55 thousandths. So it's pretty small, right? 0.055, 55 thousandths of an inch. Yeah, pretty small. Now, you're going to get all different kinds of limits for deflection. So if it's a mechanical machine system, deflections can be really like they just don't want stuff to deflect at all. Typical floors, like if this was a beam for a floor in a residential or commercial building that the public's going to use, 1/300th of the span is very typical limit. 1/300th of the span. So our span was how many inches? 120. If I take 120 and divide by 300, that's 1/300th, right? That's 0.4 is a standard typical allowable deflection. Yeah, almost half an inch, but that's under full loading condition. Yeah, so like in your residential home, full loading condition is like 200 pounds per square foot. It's like 200-pound people standing shoulder to shoulder in your home. That's when you get the 0.4. When is that? Well, I guess if you have a big mosh party or something, you know, and everybody's like jumping up and down, that's how you break stuff, right? Yeah. So you can get there, like it can happen for sure. But 1/300th of the span is a pretty typical limit. And we're way under that, right? Which I don't know, if you think about, that's pretty impressive for wood to carry 16,000 pounds. It's a big beam, I know that, but still, that is a lot of load. Yeah, and it's hardly like, it's not even phased by it, really. There it is, the whole problem. No, and we even had a fail in there, like the bending stress failed, so we had to go through a little design process to figure out the new beam. And then we carried on and did the shear, that was good, and then we did the deflection, no problem there. Okay, so the formulas are really good, but they get really hairy, like they get crazy, so you got to be really careful with them. Just looking at some of them. Where's a cantilever? So here's a fixed cantilever. Where's a straight up cantilever? That might be the first one. Nope. Yeah, here it is. So cantilever beam, concentrated load at any point. This one I've used a lot. So concentrated load, it can be anywhere, right? It's at a distance. So the equation for maximum bending is not too bad, but then bending at other locations, it just gets, you got to be really careful. Like there's lots of opportunities for mistakes.
With our problem, we got the delta max is 0.055. What was the level is the span over
300, yeah, 1/300th the span.
So and we got 0.4.
Yeah.
So
0.4 for the allowable, right?
the allowable.
Yep.
So for whatever reason we want to decide, figure out how much weight they need for not allowable.
Yep.
You would plug P in for the 16,000.
Yeah, so that, yep. That would be designing by deflection. You 100% got to go check the bending stress after that, because it could fail easy in bending stress, right? So to load something up to that allowable 1/300th, you'd always have to go check the bending stress. That's why we typically don't design in deflection. We design in bending stress. So when we hit bending stress and it failed, we went ahead right there and used this bending stress equation to pick a new beam. That's what I mean by design in the bending stress equation. Then check everything else, check shear, check deflection.
But there's no reason we ever need to go back to the beam on the canvas hole.
Not normally. I mean, there's always, you know, possible scenarios where you want to know because they're adding stuff or changing design above something. 200-year storm instead of the 100-year storm. But yeah, we typically design in the bending stress equation, then check everything else out. Like if this was a design problem, we didn't know this, right? We still would need, you need the material. There can't be too many unknowns. Like you can't say, oh, I don't know what beam I'm going to use and I don't know what material. You can't design. That's not a thing. So you have to know the load condition. You have to know the material. You maybe don't know the cross section, right? So you would go through the statics part and then you would use the bending stress equation to make a choice. That's why you say first choice, because sometimes it'll fail in deflection. You go to check the deflection, it's like, oh, that's way too much deflection. So now I have to make a second choice based on maybe deflection and then go back and check it in bending. So it's a little bit of a dance, and it can get, you know, when you don't know for sure what's going on with the material or the cross section, then you can go through it a few times before you get everything to work out. Deflection again. Yeah. Yep. We'll just do more. Well, that's deflection by formula. So deflection by formula would mean that your beam matches one of these. Well, what if your beam doesn't match one of these? Then it's like, oh boy. Yeah, it's called the area moment method. You have to create the diagrams, and then from the diagrams, you create a deflection curve. And then from a deflection curve, you can do some trigonometry to figure it out. So it's rough to do, and it's not done very often. I've never had to do it. So, yep. Yeah, and most often you just use straight up span tables. Like there's span for wood. So I've done most of my work I've done with wood. The stuff I did with steel, then I had to do it all like this. But even if you have a more complicated beam that maybe doesn't match perfectly, you can do deflection by parts. So you can say, oh, I have a concentrated load and I have a fixed end and I have a distribution. None of it works. Like there's no beam that is like that, but there is a cantilever on its own. And if I find that the maximum deflection for that thing is at this location, and then I do the distribution and it's at the same location, and then I do the concentration at the same location, it's like, do them individually, add them up. Yeah. And then other times I've had beams that are just so close to the existing beam that I'll run the number from the formulas. And if it's like not even close, I'm like, it's good. And you make that decision. I mean, you make those kind of decisions all the way through because nothing's going to match perfectly. So at some point you just take some experience and say, oh, this is good. I've run enough numbers to know I'm pretty confident this is good. So, and that's the other thing you can do is if you're not confident, you can add a factor of safety. And then if the numbers work, it's like, oh, now I'm really good. Probably too good. Like probably costing more than it should, but you know what? It's not going to fail. No one's going to call me. So it's not a bad thing. All right. That was good. That's definitely enough. And then I think your homeworks will make you do a little bit more. 1905.
It got burnt down in 1964, apparently.
Oh, it's a log?
Yeah, look at how those are kids, but I mean, those are still pretty big logs.
How big was the thing?
I don't know. My buddy sent it to me today on Discord, and I was like, damn, it's pretty wicked, but yeah. apparently it burnt down.
Unbelievable. That is not a cabin, man. That's a lodge.
In 1905 too. How did they get those there and like in the right place? Like
1905.
would've been smart.
That's horsepower, like the real thing. Horse and
Yeah.
pulley. You can do amazing things with.
Imagine doing the statics on that problem.
Yeah.
Nah, it'll work.
Completely. Well, most of that stuff is just so completely massively overbuilt
Okay.
that it held up fine.
Yeah, I figured all those wood logs aren't gonna break or nothing. But man, I wish it was still here to go look at.
Yeah,
it,
no
'cause,
kidding.
man, yeah, I'm gonna have to look at it.
That's,
Uh-uh.
yep.